Example 4 says, find the indefinite integral of the square root of x squared minus 1 over x dx. Going back and looking at our table of trig substitutions, because we have something of the form the square root of x squared minus a squared, we are going to let x equal secant of theta. In this scenario, our a value is 1, so that's why the coefficient of secant is 1. And then if I take the derivative, we get dx is equal to secant of theta times tangent of theta d theta. So let's go ahead and rewrite our original integral. We're going to have the square root of secant squared theta minus 1 over secant of theta times secant of theta times tangent of theta d theta. This one's nice because underneath the square root we don't have to factor out a constant, and we could just change secant squared theta minus 1 into tangent squared theta using our Pythagorean identity. So this becomes tangent squared theta. And then also we can see that this secant and this secant will cancel out. So we are left with the square root of tangent squared, that's tangent of theta, and then times tangent of theta d theta, and this is equal to tangent squared theta d theta. Now, using one of the forms of our Pythagorean identity, I know that tangent squared theta is equivalent to secant squared theta minus 1 d theta, and I can split that up into two different integrals. The antiderivative of secant squared is tangent of theta, and then we get minus theta plus our constant of integration. So now what we want to do is we're going to draw our right triangle. Here's theta, and I know that secant of theta is equal to x. If I take the reciprocal of both sides of that equation, that's going to tell me that cosine of theta is equal to 1 over x. So my adjacent side length is 1, my hypotenuse is x, and then my remaining side length, the opposite side length, is going to be the square root of x squared minus 1. So coming back over here, tangent of theta, we can see from the picture, is the square root of x squared minus 1. And then if I wanted to solve for theta, I could use several different inverse trig functions. For example, here, if cosine of theta is equal to 1 over x, then we could solve theta ends up equaling cosine inverse of 1 over x. From this equation, we could also use theta is equal to secant inverse of x. That's another possibility. I'm going to end up using tangent inverse since we already have tangent over here, and then plus our constant of integration. So again, just to emphasize, this angle that we solved for, which was theta, we could have similarly used cosine inverse of 1 over x. Another possibility we could have used was secant inverse of x. And there are definitely more choices than that, but these are some possibilities we could have chosen. Example 5 wants us to evaluate the indefinite integral of the square root of x squared plus 2x dx. Now, if you look at our table of trig substitutions, the way that this is written doesn't really appear in our table, and it has to do with the fact that we have plus 2x. And remember, the three main forms we're looking at is the square root of x squared minus a squared, the square root of a squared minus x squared, and then the third one is the square root of x squared plus a squared. And so this original integral that we have doesn't really model or fit any of those cases. So what we're going to need to do is we are going to need to complete the square. And if you don't remember what that is the process of taking a quadratic function in standard form and changing it into vertex form. So to reiterate, completing the square is going from standard form of a quadratic function to vertex form. And the way that we go about doing that is in standard form, we have our b value here. And what we're going to do is we're going to take b divided by 2, and then we're going to square it. So looking back at our original radicand, we have y equals x squared plus 2x, or you also don't need the y equals, so we could just write x squared plus 2x. So our b value in this case is 2, so I'm going to take 2 divided by 2 and square it, and that's equal to 1 squared, which is equal to 1. So what that means is, what I want to do is I want to add 1 at the end of my quadratic, but I can't just randomly add 1, that will change my function. So to counteract that, I'm going to subtract 1. So now by adding 1 and subtracting 1, I have essentially maintained balance. It's still the same function, but now these first 3 terms, I'm able to factor that into x plus 1 squared, and then I'm bringing down the minus 1. So my original integral, I can now rewrite as the square root of x plus 1 quantity squared minus 1 dx. And now this is in the form of some variable squared minus some constant squared. And now we're going to be able to use one of our trig substitutions. Okay, so from here, now what we're going to do is, because x plus 1 is the thing that's being squared, I'm going to say let x plus 1 equal, and then if you look back at our table of trig substitutions, I'm going to rewrite this as our a value is 1, so it's just going to be secant of theta. And from here, I can still take the derivative, and because I have plus 1, the derivative of a constant's 0, so I'm still going to end up with dx on the left side, and then on the right side, I'm going to get secant theta times tangent theta d theta. And so now we can rewrite this as the square root of secant squared theta minus 1, and then dx we can replace with secant theta times tangent theta d theta. And secant squared theta minus 1, that is equivalent to tangent squared theta. And then I can take the square root of that. So we'll get tangent theta times secant theta times tangent theta d theta. And then that gives us tangent squared theta times secant theta d theta. From here, what I'm going to do is I'm going to rewrite tangent squared using one of the Pythagorean identities. So we get secant squared theta minus 1 times secant of theta d theta. And from here, what I'm going to do is I'm going to distribute secant of theta into my parentheses, and that's going to give us secant cubed theta minus secant of theta d theta. Now I can split this up into 2 separate integrals, so that's going to give me the integral of secant cubed theta d theta minus the integral of secant of theta d theta. So these are 2 classic integrals in terms of trig integrals, and unfortunately for my students, this is a homework question. So I'm going to leave you to solve that one on your own, but I'll give you a hint. You're going to use integration by parts, so you're going to rewrite secant cubed as secant squared times secant, and then d theta, and then you're going to use integration by parts on that. So I'll leave that up to you in terms of homework. Let's go ahead and solve this second integral. And the classic way that you do this is, as it stands, I can't really do much. So I'm going to multiply this by a fancy looking 1. And the fancy looking 1 is secant of theta plus tangent of theta over secant of theta plus tangent of theta. And then I still need my d theta here at the end. And the reason that we're multiplying by this fancy looking 1 is now this is going to allow us to do u substitution. So I'm going to let u equal secant of theta plus tangent of theta. And that's going to imply that du is equal to secant theta times tangent theta plus secant squared theta d theta. Okay, so notice now if I distribute secant into both of these terms, that's going to give me secant squared plus secant times tangent d theta. And so it turns out that my entire numerator, including the d theta, all of that is going to get replaced with du. So now this integral here is getting replaced with du over, and then our denominator happens to be u. And we've done this several times now. This is equal to the natural log of the absolute value of u plus c. And then I can go ahead and sub in my u value. So I get the natural log of the absolute value of secant of theta plus tangent of theta, and then plus c. Okay, so at this stage, let's go ahead and, although I'm leaving it up to you to integrate secant cubed, for homework, I will give you the final answer for that integral so that we can solve the rest of this question. So the integral of secant cubed theta d theta is going to end up equaling 1/2 secant of theta times tangent of theta minus, or excuse me, plus 1/2 times the natural log of the absolute value of secant of theta plus tangent of theta. And then that completes the integral of secant cubed. Now we're subtracting off the integral of secant, which we found here. So I'm just going to copy that down. And notice that this term and this term are like terms. So I'm going to go ahead and combine those. Because they're like terms, we get this. And at this stage, we can start to draw our right triangle. So originally what we did was we said let x plus 1 equal secant of theta. And if I take the reciprocal of both sides of that equation, I'm going to get cosine of theta is equal to 1 over x plus 1. So that means that our adjacent side length is 1 and our hypotenuse is x plus 1. And then if we use the Pythagorean theorem, or if we look back at our original integral, the opposite side length is going to be the square root of x squared plus 2x. So now we want to use looking at our right triangle to figure out how to get our answer back in terms of x. And so we have 1/2 secant of theta we knew from originally is x plus 1. Tangent from looking at our picture is the square root of x squared plus 2x. Then we have minus 1/2 times the natural log of the absolute value of x plus 1 plus the square root of x squared plus 2x, and then plus our constant of integration. So here is our final answer for this question.